Hello, Charlie.
Oh, hi there, Ben. How are you?
I'm very well. How are you today?
Yeah, very good, thanks. Very good.
Loving the car. Is this electric?
It is, yeah. It's pretty new, and it's taken me a while to get it because I've been looking for a right model that I'm actually able to park on my drive.
Has that been a problem?
It's been a real problem. Do you know what? I reckon about 25% of people on my road can park and charge off street. The rest, they've got to use public infrastructure like this.
Well, like these things.
Yeah, yeah.
God, that's been a problem for them.
Well, I think the challenge is, where do you put them? How many do you need? How fast are the chargers? Who's going to use them?
Do you think anybody's got the answer to that?
Well, I think it's going to be a big debate and there's a lot of work going into it.
Really? That seems like a real challenge because you don't get the right number of these, then you're not going to get the right number of these.
Absolutely. And people won't make the transition.
God.
And that includes people like me, but also people who use cars for business as well.
Blimey. Well, that's a real problem. Is that the big problem?
Well, I think there's a bigger problem.
Tell me.
These houses over here.
What's wrong with those? They look like nice modern new houses.
Well, in terms of this area, they're going to contribute a third to a half of the pollution.
Blimey, that's huge.
And they're all on gas.
Oh, of course. So do we know where they all are? Do we know how much gas they're producing?
We do.
Really?
We can calculate that.
Really? And how do we do that?
Well, there's some technology that we work with that's really clever. That's able to profile all these different housing stocks.
Of course, because it's a spatial problem, isn't it?
It is a spatial
But
problem.
lots of complex and difficult data to pull together.
Yep, lots of different sources, bring them together, some of them public, some of them our own sources, and there's some great technology that we use to do that.
So Charlie, if everybody could use that, then we'd have the answer. Charlie, so tell me, what is that technology?
FME.
Right, so after a great introduction like that, hopefully you got some idea what we're trying to do here. We fundamentally believe that your skills in FME enable you to provide solutions that will make a substantive change in our attack on climate change. You can make a difference. And what I'd like to do in this session is go through how we've approached this, how our FME skills are enabling us to start to make substantive changes, and how that might help you in what you do. So that's kind of the core of it all. I'll give you an overview of where we are, overview of our approach, and then I'll go into detail in one of our projects. So climate change is a real thing. Some don't believe it. I do. It's a fundamental change. And even the United Nations is saying it's the greatest threat to mankind. And it's something that's affecting all of us all the time. All of us are already getting hit by atypical weather. We're getting fierce storms. Even Vancouver is having droughts. It's a real problem that we need to face, and it's our generation that needs to face it. Our children are going to pay for this, and our grandchildren are especially going to pay for this. And how much it affects their lives is very much down to how we respond to it. So we have a responsibility here to do something. And I don't mean do something about just being nice, about turning your lights off, about maybe changing the way you fuel your house. These things are all important. But actually you, with your particular skills, can make substantive changes. You personally can help drive this forward. And I think it's something that we really need to be thinking about. So why do I think you can do that? Why do I think it can make such a difference? And it's because, to be honest, the solutions to climate change are really effectively large spatial data problems. And it's significant spatial data management that will provide the answer to a lot of these problems. So I'll just go through a humdrum example and we'll see how it tumbles out. And hopefully that will give you a view of what I'm talking about. So let's do something simple. If you were a municipality, an authority, how many chargers should you install? So should it be 5? Should it be 10? Should it be 1,000? And where should you put them? It's a simple question in many ways. You've got some EVs, you've got to put some chargers in. But actually, when you start to dig into it, it gets a little bit more complex. And before you start sticking millions of pounds in, you're going to have to get to a minimum level of information. in order to have an effective rollout. So let's just think about some of those questions. So those questions could be, how many people and cars are there in my area? So that's relatively straightforward. Who's already next to a public charger? Okay, I think we can start spinning out some sort of Esri isochrone kind of thing for that. That's not that hard. How many people cannot park and charge at home? Well, that starts to get a little harder. That starts to get a little bit more complex. Of these, how many people have access to public charging? So now I'm trying to understand what the individual characteristics of everybody's individual households are. And if I put a charger in, who would get access to what? And what sort of different people would need access to what sorts of different chargers? Hang on, this is getting quite difficult. And what should my rollout look like, given the access to electricity, to power, to infrastructure, to need and demand, to flow, to early adoption and late adoption? This is all starting to get really, really, really complex. And if you think about spatially, how you would answer that, if you've got basic GIS, you could do maybe the first or the second of these questions. But unless you've got FME, you're going to really struggle with the rest. And we're answering this for a whole chunk of customers, for authorities, because they don't have that advanced spatial capability that you have. This difficult combination of spatial data sets going down to centimeter squared analysis and then aggregating that up nationally, combined with many, many different data sets, spatial data sets and what we like to call non-spatial data sets, all tying together, data sets that were never designed to tie together, coalescing them all into one whole to be able to give you this answer. If you don't have FME, how do you answer this? But then the other question is, if you do have FME and you can drive FME, imagine how many of these sorts of questions you could answer. So is it just about EV charging? If we do charging, is that all we're talking about? Not really. There's a whole chunk more. So give you a view of what we're looking at. So this is UK data. As you might have guessed by now, I come from the UK. And it's megatons of CO2 equivalent. So you could all call them GHG, whatever. And you can see the graph types of what the different types of contributors are. And in the UK, our biggest contributor, single contributor, sector contributor to CO2 tonnage equivalent is service transport, then industry, then buildings, then power. And what we've noticed, and we're answering clients' questions for all of these, is the questions are incredibly similar. What's the demand? Where do I need to put infrastructure? Where is demand? Where does the infrastructure need to be? What sort of infrastructure do I need to support that demand? When do I need it and at what cost? And we're doing this for public transport. We're doing this for decarbonisation of heat. We'll talk about that in shortly. We're doing this for the retrofit costs. So if I've got a building and I need to move it to heat pumps, then what do I need to do to the building fabric so it's ready to go to that? How will hydrogen come into this? Where does hydrogen supply need to be? Clearly, it's much easier to have hydrogen supply right next to the coast, because that's where you can get your wind turbines to generate it. But then how far in from the coast should the hydrogen come before we move over to electric? What does that look like? What does that profile look like? How can supply chains be moved? If we're going to go through this whole element and we're starting to look at vehicles with potentially different types of range, then we're now starting to think about fueling in a different way. We're starting to think about supply chains in different. How would we do that? And if we're going to start to do this, then we're going to start to go to a dispersed energy ecosystem. And so we're going to have local energy, and how far does that move out and what does it deliver? It is all about what are all the different data sources and how do I bring those all down to where? And if you think about the things I've just spoken about, how on earth do you answer that without FME? So that's the concept, that's the background to the conversation today. And what we'd like to do now is I'm going to hand over to one of our partners, Charlie Gilbert, and he's going to take you through what we're doing is just one of these use cases, which is how we do decarbonisation of heat and understand the impact of that on the electricity network. So we'll go through that use case, and hopefully that give you a clearer view again, how you and your ability to drive FME and the FME software itself can actually start to create these substantive changes. So hope you enjoy the presentation, and I look forward to catching up with you at the end.
My name's Charlie Gilbert, and I'm a partner at MISO, and I'm joined by my colleague John Britton, who's a software engineer. And in this session, we're going to talk to you, following on from the initial video that you saw, a specific customer challenge around the adoption of low carbon technologies. We'll take you through a bit of a solution flow, and importantly, we're going to delve into a bit of detail in terms of how we used FME on this particular project. So I hope you guys find it really interesting. So we'll get started. Now, with 2050 net zero targets being introduced around the world, there is a key role to play for the power companies, the network operators. The decarbonisation of heating in our homes will be a huge step towards the UK's goal of net zero by 2050, and we'll see in a minute why this is important, Scotland by 2045. And heat in buildings, just to give you a view, is currently responsible for about a fifth of Scotland's greenhouse gas emissions. However, in a world where generation, transmission and consumption has followed similar patterns for the last 50 years, there's going to be some big changes, and the rulebook's really being ripped up. And the arrival of these new low carbon technologies brings specific challenges to network operators. And we're going to talk today about one of the customer projects that we've worked on for SP Energy Networks, who is a DNO in the UK, and they are responsible for delivering power to about 3.5 million customers in a couple of areas of the UK, one in southern Scotland and the other in North Wales and Merseyside. So there's now a need to understand in a much more granular way where demand for these new low carbon technologies is going to arise and how it's going to affect consumption. What's also hard is a lot of the potential changes could catch these types of organisations off guard because they don't get notified about these new technologies coming online. And also, because of the speed of adoption, they could also come at scale. Now, fortunately, change doesn't happen overnight. So there's an opportunity now to prepare these organisations and informing them how they're going to be able to handle these new forms of low carbon heat and electric vehicles. And we're going to focus specifically on heat in this area, in particular, looking at the transition from gas and oil to electric heating. And that's going to be electric radiators, heat pumps, and also district heating. And of course, all of this is going to add incremental additional demand onto the network that wasn't there before. As we said, many of these houses are on gas or oil for their heating source. So to counter this challenge, SP Energy Networks need to have a fast-paced, accurate forecasting model so they can work out investment plans and specifically where to put reinforcement into their infrastructure. And it's a very spatial problem. And in a regulated industry, these organisations have very strict SLAs to adhere to, with significant penalties if they're not met. So investments need to be delivered and justified by the regulator, which in this country is an organisation called Ofgem, who also sponsored this project through its funding initiative. Now, one of the key levers that affects the pace of change is the impact of government legislation. Now, as we don't know when and how this might occur, SP Energy Networks needed to understand a number of scenarios and how this will impact their network so that investments can be delivered at the right time and in the right place. Now, in Scotland, where SP Energy Networks has 2 million of its customers, the Scottish Government's published its Heat in Building Strategy consultation, and that includes plans to invest £1.6 billion just in the next Parliament, with the aim of 1 million homes to be on zero emission heating by 2030. Now, this is going to have a significant effect on the network of cables and substations. And as I said, it's a spatial problem with multiple data sources that need to be crunched together to assess the impact of where this is going to happen. And this is where FME played a really valuable role. So, who does the decarbonisation of heat affect? Well, in reality, it affects everybody. What we looked at in this project are a range of adoption use cases covering different forms of housing, of different sizes, with different ownerships, using different types of heating adoption. So there were quite a lot of calculations that needed to be undertaken, measurements, analysing detailed data so that we could understand where and how this scenario could occur. And it's a scale of challenge model. We need to look at network reinforcement, but first of all, before we do that, we've got some more basic fundamental questions to try and answer. Where are the houses? Are they big ones, small ones? What's their level of insulation? Are they flats? Are they large country estates? Are they 1970s semi-detached buildings? Recent housing developments? We then need to look at the propensity for who's going to adopt, who's more likely to adopt, and what drives some of those adoption behaviours. And one of the key challenges that we had with this project from a data perspective was that there wasn't a single golden record. There were multiple data sources, some of them open data, some of them proprietary data sets. We had some socio-demographic data that we needed to work with. We needed to aggregate the data up from very granular household level right up to postcode geographies and other operational geographies so that the business could have an understanding of how that fed into their infrastructure. And then once we did the modelling, we also needed to feed the outputs into some specific software which understood the network topology flow to understand at individual substation level how that model was going to impact specific elements of infrastructure. Now, in many projects that we work with, there's lots of industry standards and data sets that are available, but with this we had to curate a number of these data sets with some limited data, and we needed to provide a robust modelling environment so that that stuck up as well. So from a project objectives perspective, what we were trying to achieve was to predict and model where these electrified heating forms came on across the network area in Scotland and in England, and look at how legislation and behaviour affected that adoption and develop a methodology for that. And coming back to the spatial challenge, taking all of that and outputting it at a household level to feed into this network flow topology modelling toolset, which came off an automated process to then look at that scenario and impact assessment. And then finally, we needed to combine the data from this project with another project, which was a sister project that we ran, not just looking at low forms of low carbon heating, but also electric vehicles to get the total sum of incremental power that's going to be used on the network, so that SP Energy Networks have that overarching view. So there were some key challenges, and just flowing into the solution flow in terms of how this fed together, the amount of electricity demand generated by these low carbon heating alternatives varies significantly depending on the type of property, the insulation level, the ambient temperature, and the type of heating used. So we adopted the following approach. We set up a core data set where properties were categorized and assigned a series of flags relevant to the calculation of their low carbon heating demand. And then we developed a calculation model which takes the user input forecast of future adoption levels and uses a core data set to calculate the additional demand for those future adoption levels. And then we output that as a dashboard and a data set. Now, the calculation model takes user input forecasts for future adoption levels and then uses the core data set to calculate the resulting additional demand. And the key steps that we took at, first of all, looking at identifying these in-scope properties, and we used some Ordnance Survey data and address data, were to identify the area property, the properties that share a building, the number of stories, the property square meterage, the number of external wards, and a number of other factors as well. And once key property characteristics were defined, we then worked with socio-demographic data where we flagged and identified properties for ownership and legal and taxation environments, and then fed that into our model, which then was a dynamic model that fed in. And FME was used across this entire workflow. And one of the areas that it was very much looking at spotting on identifying and then smearing the demand across these various different housing types. So it's just not possible, it's not viable, it's not robust enough to be able to say that we know exactly where this particular property is going to have a heat pump at this particular stage in its life cycle in time. So we smeared all of the demand and had the concept of a heat fraction that we smeared across some of those additional areas. And then we realized all of this on a platform interface. So I hope that just gives you a bit of a summary of the key steps and a bit of background to the project. One of the really key things that we wanted to stress in this presentation was how FME was fundamentally an important tool to address these some of the challenges that we looked at on the project. And there's 4 key areas that we'd like to share with you in a bit more detail. And I'm going to hand over to my colleague John Britton, who's going to talk a little bit more about that in detail.
Thanks, Charlie. So throughout this project, we've faced a number of technical challenges, and FME has been invaluable for helping us meet a lot of these challenges and ultimately deliver the project. The first one I wanted to talk to you about was that before we can predict energy demand, we first need to know the property types and floor areas and number of stories for every single household in the SP Energy area. So this is a lot of data we're talking about, and it equates to about 3.5 million households. We also want the process to be robust enough so that we can scale this up to a national level if we need to, which is another 28 million households. And all the while, we don't want to worry about resource usage. So we don't want to have to increase the amount of hardware we're using to process this at national level. And we don't have to worry about the process falling over. So our approach to this problem was to break it down by splitting the target area into separate spatial tiles and processing them separately. To achieve this, we use a combination of a parent and child workspace, which we run through FME server, where the role of the parent is to orchestrate the running of the jobs, and the child is responsible for doing the actual spatial processing. So each time the parent is run, what it essentially does is selects a fixed number of unprocessed tiles and queues jobs for those tiles, and then finally will queue itself before completing. And this just happens repeatedly until all jobs are completed and all tiles are processed. The good thing about this approach is that it means that every individual job is short-lived, and we don't have any specific jobs hogging engines. The parent isn't sat there hogging an engine where we could be using it for spatial processing. Everything's used for spatial processing. And another benefit is that if a higher priority job comes in that we didn't expect, it can still get processed on the same FME server. So this doesn't get in the way of our day-to-day processing jobs. FME's helped us for this challenge in a number of ways. So firstly, obviously, we all know FME is great for the complex spatial processing elements, but it's also allowed us to break down our workload into manageable chunks and orchestrate the processing of those chunks in a way that is scalable. And additionally, it's also easy for us to rerun the process. So if we wanted to run it again for a different geographical area or nationally, all we need to do is swap out the input tile grid and we're good to go. And we just run the same FME process again with no issues there. The next challenge I want to talk about was the processing of many disparate data sources. So the nature of this project meant that we need to combine lots of data from lots of different sources, and we need to combine this data into a single primary input data set for our predictive model. So the source data we're dealing with includes a number of different spatial data sets, such as OS data, including mass map and address space, the SP energy, districts and regions, LSOAs, the tile grids I mentioned previously, as well as some non-spatial data, such as the off-gas statistics for properties, the demographics and tenure. And these come in various different input formats too. So we've got spatial databases, we've got spatial files such as tab and shapefile, Excel and CSV and so on. In addition, we've also got various different levels of aggregation. So some of the input data is at property level. So we have 3.5 million records per dataset. Some of it's at building level, some of it's at postcode level, some of it's at LSOA level. And we need to combine all of this variety of data set together into a single file that we can use for input into our predictive model. So again, FME was invaluable for us here because, firstly, it supports all these formats natively. We don't need to worry about writing any code to read any strange file formats or anything like that. And once the data is in FME, it allows us to merge the different levels of aggregation seamlessly. Using things like feature joiners, or for spatial joins, we've used quite a lot of point on area overlays. And finally, the resulting workflow is easy to follow and communicate amongst the team, which we found really useful too. So the next challenge I wanted to dive into was prototyping. So early on in development, we needed to quickly prototype and run early versions of our predictive model and communicate results with the customer. Although the final model was always going to be written in code and deployed to our accelerated insight platform, we didn't want to commit to the development of the model until we bottomed out all of the requirements and were happy with the methodology. Also, it was far less important at these early stages that the model be quick to run. In production, and in the final version, we wanted to be able to run in a couple of minutes for the whole 3.5 million records. But at this point, it was way more important that the model should be quick to develop and update as more requirements came in, and we wanted to experiment with different approaches. So for these reasons, we built our first prototypes using FME. And this was great because FME allowed us to quickly tweak our methodology by switching out transformers or introducing new flows to our workspace. And it also allowed us to inspect the data as it ran through, which allowed us to debug not just the workspace, but the methodology itself. Another great thing is that the FME workspace was self-documenting. So if we use bookmarks correctly and annotations correctly, we can actually use the workspace itself to communicate the methodology amongst members of our team, which is particularly good for us because we've got a lot of in-house FME knowledge, but not everyone's a programmer. So we made sure everyone was up to date and knew what we were doing. And finally, when it came to actually implementing the model in the cloud, we had the FME version of the model there ready for regression testing, so we could run the same scenarios through FME and then run the same scenarios through our cloud-based model and essentially expect them both to produce the same outputs. And if they don't produce the same outputs, we know we've got an issue and we can track that down and fix any bugs. Finally, I thought it'd be nice to drill down into a more specific technical challenge. And this is linear regression and how we've implemented this in our FME prototype model. So our predictive modeling methodology uses a lot of linear regression to predict energy uses for each household. I won't go into too much detail, but essentially we trained a load of linear models outside of FME on thousands of training data points. And the output of this is essentially a number of coefficients and intercept values, which can be used along with the specific household values to predict energy usage for each property. The way this is implemented in FME is as follows. So these coefficients and intercept values are passed in as private parameters. So as you can see, there are a number of private parameters for coefficients and intercepts. If I take annual demand as an example, the coefficients you can see are passed in as essentially just a big comma separated string. And the way that's used in the workspace is each of these sets of coefficients is passed out into list attributes. So each set of coefficients you get a list and you get access to the individual values when it comes to actually doing the linear calculations. So to do these linear calculations, essentially each input feature runs through this attribute manager, and this attribute manager carries out a number of mathematical function calculations. So again, heat demand, if I use that one as an example, you can see we're doing a very, very large calculation, which pulls in the input coefficients as well as the actual values for each property. And the output of this giant function will essentially be the predicted value for annual heat demand for that property. And we do that for each of the other values we want to calculate. And all 3.5 million properties run through this, and we get predicted values for every single one. So to summarize, FME has been really useful in this project for a number of ways. So it's allowed us to manage our huge processing workloads and make them more manageable and scalable. We've been able to integrate lots of disparate data sets into a single workflow without any issues with data types or formats or aggregate levels of aggregation. We've successfully prototyped our model in a way that was quick to develop, modify, and debug. And also the workspace is self-documenting and can be used to communicate our ideas and methodology amongst the team in an effective way. If you have any questions about how we used FME in this project or any other of our net zero projects, please get in touch. We'd love to hear from you. Now I'll leave you with Ben to wrap things up.
Okay, so I think we've talked about the challenge. We've talked about how FME ties into that challenge, and we've gone in detail actually the real life impact on a real project. And hopefully you've got a view about that, and in your mind you're going, that would be a horrendous project to do that FME. But with FME, we can see the power of what you can achieve. So how can you help? What can you do? So I don't know what organization you come from. And even if I did, I'm not going to be so patronizing to tell you how to tell you what to do. That's not what we're here for. What I will do is I'll talk you through the stages that we've done, what we've done in order to go down our path. I think the first and the crucial difference is, rather than measuring our business on P&L and on financial metrics, we decided that there were some basic finances we had to get past. Obviously, we have to be a sustainable business and or self-sustaining. And then after that, then what we decided was, actually as a business, we had to make a difference. And the most fundamental and most important thing for us is to make a difference. And if we change that focus, and we did this a couple of years ago, then actually the entirety of our business starts to change. The second thing we did is we understood that actually all of our customers are struggling in a very similar way with how to provide solutions, how to counter climate change. And actually the fundamentals of this was complex data and spatial brought together. That's what made that difficult. So we started to talk to our customers about those challenges in that way. And suddenly a whole variety of projects that were never viable before suddenly became viable. Third, what we did is we started to build on those projects, but also take the learning out of that and start to publish them. So this gives you an idea about some of the clients that we're helping transition. But the thing that really made the difference was we realized actually that because we're very strong in FME and because the software itself is so powerful, we can actually start to aggregate information that other people couldn't, and we could publish it. So we don't keep all of this data. For as much as possible, we publish as much of our findings as we possibly can. And there's a link in the bottom left-hand corner for one of the websites we do. We've published where the 27 million households are in the UK, what percentage of those can or can't park next to the house, what percentage that is by different authority, and how much access those different groups have to public charging. And we just published all of that. Maybe you could most probably sell it. I suppose you could sell it, but we decided not, because by publishing that, we helped these authorities to understand where they were and move forward. We made a difference. And then the really nice corollary of that is that actually by informing the debate, by publishing this information, by creating all of these white papers, actually even more of those projects that we didn't know of before started to surface. Even more clients that we'd never met before started to come to us and go, now I can understand what you do. Now I understand the power of spatial when we are looking at this challenge. Actually, for our use case, which is slightly different, you hadn't heard about that before, we'd love you to come in and start to deliver that. And that's really starting to snowball for us, where actually project after project, we are starting to make a significant difference. So will this all work for you? Is this the right thing for you to do? I don't know. But I would hope that perhaps this session today has helped you perhaps look at those unique skills that you've got and give an idea of how you might be able to exercise them. We would, of course, be delighted to talk to you if you are looking to go down this path. If you want to understand more on this, there'll be some more contacts on the following page, and really happy just to chat to you through. And if you want to achieve some of this stuff, we can give you some views and pointers and all that kind of stuff. Very happy to share. The more we share, the better. So good luck. I hope this helps, and good luck in addressing climate change. Thanks very much.